All right, hi everyone. Welcome back to section 6.1. And in this video, we are finally at the point where we're going to be able to solve a differential equation. Okay, that's the whole point of this class, being able to solve differential equations. And so we've been learning and reviewing some power series concepts and tricks and trades in order to get to this point where we can solve a differential equation. Okay, so we're going to use the ideas of power series to figure out how to solve the differential equation. Because remember, our goal is to get y equals something, right? That's how we solve a differential equation. And so the way to do that with power series is we want the solution to be of this form right here, right? It's a little different than what we had before, where it would just be y equals some function, but we want y to be a solution of a power series. So the solution would be, c to the n, x to the n of some power series. So, usually when we have these solutions, there's a specific method we go about trying to solve them. And so the way we do this for power series is we always set up our initial trial. So here we go. Let's go ahead and try it out. And we'll say solution. And we will set up our trial solution, which is that given y equals the series starting at n equals 0, c sub n, x to the n. So we're going to use this as our trial solution. And what do we need to do? We need to plug it back in to the differential equation. So we're going to plug it back in for y, and we need to plug it back in for y prime. So what do we need to do? We need to find y prime. So we'll also need to find y prime. And so what does that look like? What does a derivative of a power series look like? So let's kind of go off on a little tangent here. Let's see what a derivative of a power series is. So let's just take the power series, right? C to the n, x to the n. All right. Let's write out the first couple terms. So C naught plus C1 x to the first power plus C2 x squared plus C3 x cubed, et cetera, and et cetera, right? Um, And so that's this power series. And, so what if we take a derivative of each term? What if we do that? So, you know, derivative of y, okay, that means the derivative of the series n equals 0 to infinity, c sub n x to the n. Well, that equals the derivative of all of these terms we just listed out. C naught plus C1 x plus C2 x squared plus C3 x cubed, dot, dot, dot. Okay, so let's look at these terms right here, right? The derivative of a constant C naught, well, that's just going to be 0. So the derivative of that is 0. Okay, and remember, this is my n equals 0 term. Well, what about C1x? Well, derivative of C1x would just be C1. That's my n equals 1 term. Derivative of C2x squared. Well, think about the power rule, right? So that would be 2C2x. and that would be n equals 2. Same thing for C3. The 3 drops down for the power rule, so that would be 3c3x squared, etc., etc. Okay, so that's like saying I have C1 plus 2c2x plus 3c3x squared dot dot dot. Okay, and so what it looks like I'm starting out at now is n equals 1. I'm not starting out at n equals 0. Okay, and what this really ends up being is y prime equals a power series starting at n equals 1 now, c sub n times n x to the n minus 1. Because what is this? Is really just using the power rule. It's like the n drops down and we subtract 1 from n. So here I'll say just power rule. Okay, so that's what y prime is for a power. That's the first derivative of a standard power series. It'll always be like this, so don't try to overcomplicate it. Just using the power rule. And so for future reference, because we're going to get into second order differential equations, the second derivative would be starting out at n equals 2 c sub n times n minus 1 x to the n minus 2. So it's just another power rule. Um, you just bring down the n minus 1 and then subtract another, 1. And you're starting out at n equals 2. But just for future reference, we're not using that now, just so you can understand where we're going with it. Okay, so we have the derivative, we have y prime, and we have y, our trial solution. Let's go ahead and plug these into the differential equation. So like how we normally would, as we've been doing this whole course. So let's say we plug in y and y prime into the differential equation. Okay, so what I end up with, I have y prime plus y equals 0. This turns into the series n equals 1 to infinity, n times c sub n. I think I'm just going to move this n in front just because the parentheses and all the n's right next to each other are a bit much. So n times c sub n x to the n minus 1. You could even use a if you want. When you start out these problems, like you could use like a sub n if there's too many like c's going on in parentheses. It's up to you. Um, Plus the series n equals 0 to infinity, c sub n x to the n equals 0. Okay, so this is our setup. So what we want to do and what we practiced so far is combine these both into one power series. So let's say we want to combine into one series. So what are the two components we need to do that? It's going to be the same starting index, and it's going to be both having the power x to the n. Because what do we want the solution to be? X to the n. So we need the same index, the same power, so that we can combine them. because we want them to be both x to the n for our solution. So what's the first thing we could do? Well, one starting out at n equals 1, one starting out at n equals 0. So what I want to do is index shift this first term to be n equals 0, so that we're both starting out at n equals 0. So let's write that down. So let's index shift the first series to start, or yeah, to start at n equals 0. So if I index shift the first series, that means I'm going to make this 0 and I'm going to add 1 to every single n inside the series. So what I would end up with is the series starting at n equals 0 now, n plus 1 times c to the c sub n plus 1 x to the n plus the series n equals 0 to infinity cn x to the n equals 0. You know what? Let me kind of break it down a little bit just in case not everyone got that. Um, okay, so we're index shifting to get n equals 0, but what I would have is, n plus 1 times c sub n plus 1 x to the n plus 1 minus 1. Okay, so what did we do? We subtracted 1, and so that means we added 1 to like every single n. Just in case that's still a little fuzzy to you, okay? But that's what we did. And so great, we both of these series start out at n equals 0 now, and they both start out at n x to the n. So x to the n equals 0, x to the n equals 0, which meets both of these criteria to combine them now. So let's go ahead and take care of that. Let's combine them. So now both terms start at n equals 0 and x to the n. So combine them into the series n equals 0 to infinity, n plus 1 times c sub n plus 1 x to the n plus c sub n x to the n equals 0. And they even have x to the n we can factor out, so we could write this as n plus 1, c sub n plus 1 plus c sub n, put some brackets here, x to the n equals 0. Okay, so we want a power series solution that looks like this, right? So what we need to do is figure out what exactly this C sub n is. We have x to the n already, but we want to figure out what the general coefficient terms would be. So there's a way to do that, and it's through recurrence relation. So let's check out what exactly that means. So now the only way this whole power series can equal zero, okay, is if the coefficient terms equal zero. So we set the coefficient terms equal to zero. So we said n plus 1 times Cn plus 1 plus Cn equals 0. Okay, so we're going to set up our recurrence relations right now. And the way we typically do that is here I'll say like note, we always want to solve for the higher Cn. Okay, so what we're going to do is solve for Cn plus 1 because that's the bigger or higher Cn. Okay, so we're going to move over that Cn to the to the right side, so negative Cn, and we're going to divide over n plus 1. So this would be negative Cn over n plus 1. And so our recurrence relation is going to be Cn plus 1 equals negative Cn over n plus 1 for n values, n equals 0, 1, 2, 3, however long it takes us to figure out what the general coefficient term is. And so why are we starting out at n equals 0? Well, n equals 0, well, that's because the index is at n equals 0. I'm pulling that from, right here. Okay, so let's go ahead and find out what this coefficient term is. So, um, what we want to do is let n equal 0, 1, 2, 3, etc. to find a specific pattern. So let's go ahead and try it out. So, here, let's plug in n equals 0 to our recurrence relation. So n equals 0. If I plug in n equals 0, I would get, I'm plugging in 0 into here, right? So I would get C1 equals negative C naught over 0 plus 1, which just equals negative C naught. Okay, so C1 equals negative C naught. So I'm just going to box that. It's not giving me a pattern yet, but maybe we'll get there. Okay, let's try n equals 1 now. So if I plug in 1 into my recurrence relation, I get C2 equals negative C1 all over 1 plus 1. which equals negative C1 over 2. Okay, but I actually do know what C1 equals. So I can plug in C1 equals negative C naught. And what I would get is negative C naught all over 2, which equals positive C naught over 2. So I like to say C2 equals C naught over 2. Okay, maybe seeing a pattern, maybe not. Uh, let's try a couple more. So for n equals 2, I get C3 equals negative C2 over 2 plus 1. So I get negative C2 over 3. And so, like the previous recurrence, I can plug in the previous term. So I know what C2 is. It's C naught over 2. So what this would be is negative C naught over 2 all over 3. And what that turns into is negative C naught over 6. And so C3 equals negative C naught over 6. Okay, so I think I'm starting to see a pattern now. Maybe you are as well. But let's try one more just to make sure. All right. So for n equals 3, I would get C4 equals negative C3 over 4 plus 1, right? Or excuse me, 3 plus 1. Sorry, it's moving a little slow. 3 plus 1, there we go. So negative C3 over 4. Uh, but once again, I know what C3 is. So this would be negative C naught over 6, the negative of that all over 4. So this would be C naught over 24. Sorry, I don't know why it's glitching like that. Um, Let me see. So this would be C4 equals C naught over 24. Okay, so I don't know about you, but I'm starting to see a pattern here. Um, 24, well, if you are a little comfortable with factorials, that's like saying C4 over 4 factorial. Okay, and 6, that's like saying C naught over 3 factorial. Just be careful with your negative. 2, I know it's not something that we typically think of, but it's like saying 2 factorial. And just negative C naught, we could think about that as negative C naught over 1 factorial. So to me, the pattern looks like C sub n equals, it's alternating, so I would say like negative 1 to the n, C naught over n factorial. And they were starting out at n equals 0, 1, 2, 3, etc. So that's the general pattern of C sub n. Oops. Okay, and that's what I want, right? So let me scroll up really quick. That's what I want here. That's what I'm trying to find in general. I'm trying to find that C sub n. So, you know, r- remember our goal is to find a solution of the form y equals the series n equals 0 to infinity c sub n x to the n. So we know what c sub n is. We have x to the n, right? We know what c sub n is now. So we could go ahead and plug it in. So we would have y equals a series n equals 0 to infinity. Okay. -1 to the n c naught over n factorial times x to the n. Okay, so I'm plugging this right into there. Okay, then we could clean couple things up, like, x to the n, -1 to the n. We could combine those two to be y equals a series n equals 0 to infinity, c naught -x to the n over n factorial. Okay, so that is our answer. We got our solution to the differential equation. Y prime plus y equals 0. So that's what our answer and solution is. So keep in mind all the things we did in this problem. It was quite long, a lot of moving parts to solving a differential equation using power series solutions. So there's always, kind of the same types of steps where we have our trial solution, and then what we want to do is take derivatives and plug into the differential equation. The second thing we want to do is combine into one power series. Okay, and that's through index shifting or peeling off. Okay, whichever route you want to take. The second thing you want to do is recurrence relation. Okay, like we just did up here, trying to find a pattern, and then finally your final solution. Okay, so that is a goal for solving differential equations using power series. So quite a long problem. Thank you for hanging in there. Once again, I annotate a lot in these videos just to like put down on paper what I'm saying, so I'm not just speaking in the air. So hopefully that helps, but in your homework, you don't have to write like a bunch of analog like this. Just go ahead and solve it how you want to. But yeah, so that's how we use a power series solution to solve a differential equation. Um, so that's it for this video and for section 6.1. Thank you for watching. In the next couple sections, we're going to learn how to solve these differential equations using power series, second order, and also different centers. Okay, this here was just centered at 0. But thank you for watching, and I'll see you in the next video. Take care.